Hello everyone, welcome to our AWM Pitt grad student seminar. Today we have two speakers. The first speaker is Rachel Morris. She is a PhD student from North Carolina State University. Her talk is Uniform Convergence Guarantees for Adversarially Robust Learning. Rachel, please go ahead.
Yeah, thank you so much for the invitation to talk during your seminar. I'm really excited to, meet some new people. So I'm going to be talking about uniform convergence guarantees for adversarially robust learning. This is just one part of the research I've done with my advisor, Ryan Murray at NC State. Okay, so just brief overview of what I plan to go through. So first I want to motivate this topic and problem that I consider. Then I want to go over some of the mathematical background. Then I will talk about the main part is the uniform convergence result for this optimization problem. And then finally, I'm going to talk about my current work, which is thinking about regularity results for these problems. So first off, one common machine learning task is to train a neural network to correctly classify some given input data. So one of the classical examples would be having handwritten digits 0 through 9 and asking a computer to sort these into the proper categories. And so for us, this is a relatively easy task. I mean, of course, there's going to be people whose handwriting maybe isn't as neat. And so, for example, like this 4 right here kind of looks like a 9. But overall, we can be pretty successful at this task. And similarly, a trained neural network can also be very successful at this task. However, some researchers, says Getty et al., observed that you can fool these neural network classifiers. And so kind of one of the prototypical examples is you can start with an image of a pig that is correctly classified by an image classifier that has some thousands of different categories that's trying to sort images into. And when you add very specific targeted noise to it, then the output image looks indistinguishable from the original image, but the classifier completely misclassifies it and thinks that it's an airliner. And so kind of what's going on under the hood here is that this noise is chosen in a way that really exploits the way that the classifier learns and moves it in some sense away from the class pig and towards the class airliner. And one other thing I want to mention here is that not only does the classifier think that this is an airliner, but because of kind of the way that it's being exploited, it's more confident that this second picture is an airliner than this first picture is a pig. So there's obviously some undesirable behavior going on here that we really want to both understand and then be able to kind of guard against. And so even kind of a step further, it's not just like kind of this artificial, you can start with a pig and then, oh, here, this pig picture, actually, the computer thinks it's an airliner. But there are ways that this can be engineered even in real life safety critical situations. And so one example from some research done by Eckholt et al. Is that you can start with a stop sign and you can add different stickers to the stop sign. And so whether those stickers are just patches or whether they form words, well, at least 60% of the time, a road sign classifier trained to classify specifically different road signs will fail to classify the stop sign correctly. And so especially in the age of self-driving cars, we really want to be able to trust that our cars will be able to get us from point A to point B and stop at the correct moments. So all of this kind of leads for the necessity to really understand these classification algorithms better, and also why this kind of unintuitive behavior and non-human-like behavior of this adversarial examples occur. So now some of the mathematical background for how I think about this problem. So first of all, I'm going to restrict our setting to just binary classification. So instead of having thousands of different image classes, we can just consider two-class classification. So for example, trying to distinguish between cats and dogs. And so this binary classification, we can think of all of our images as being represented in the space RD just by some long vector. And then each should have an associated label, 0, 1, where again, 0 we can think of as the category cat, and 1 we can think of as the category dog. And so we have some like large database of different images. And so we can imagine sampling from that database in order to train based on a probability distribution given by mu. And so if for a second we forget about our goal of trying to build in this, we call it robustness to adversarial perturbations, then this is just the Bayes classification problem. And so the Bayes classification problem, it says that we are trying to minimize over some subsets of RD a misclassification score J0, where J0 is going to be the expected value according to the distribution mu of the difference between the assigned label that's encoded by the characteristic function 1ax and the associated label y with the data point x. And so why are we able to just think about subsets of RD? Well, that's because in binary classification, all that you need to do is say which part of your space represents everything that is labeled cat and then everything else automatically would inherit the label dog. So it's just kind of A and A complement is all we need to define. And so in addition to kind of this big probability measure mu, it's going to be more helpful to consider the conditional first marginals. And so that's going to be row 0 and row 1. And you can think of these as being kind of the proportion of a given set A that you would expect to have the label 0, and then the proportion of the set A that you would expect to have the label 1. And so we think of these both as kind of measures and set functions, but you can also think about them just in terms of the density for a specific data point, meaning that row 0 for a specific image will just tell you how likely you think that that image belongs to the class cat and how likely it is to the class dog. So if you see kind of a row 0 or a row 1 applied to just a point, I'm thinking about it in terms of densities and not as a measure. And so also, just like in case you are less familiar with that expectation notation, this can also be written as an integral. So you integrate over the entire space, RD cross 0, 1, and then you integrate against a measure d mu. And so to try and understand this a bit better, let's just think of this toy example. So consider a density given by row 0 minus row 1 is equal to x1 times x2. And so what we have here is that anytime that difference is positive, sorry, actually, I think it should be row 1 minus row 0. I can't actually see what it says because there's something over it on my screen right now. But either way, it should be row 1 minus row 0 is equal to x1 times x2. Then everything that you want to assign label 1 should be when that product x1 times x2 is positive. And so that will be exactly the quadrant 1 and quadrant 3, because that means that for those images that belong to these two quadrants, then they are more likely to have label 1 than they are to have label 0. And so we can represent A0 star as the optimal Bayes classifier, and it would be exactly those two sets. And so now let's think about trying to add in some amount of robustness. This is called the adversarial training process, and the idea is that at training time, we include some sort of adversarial perturbation in the training process. And so first of all, you need to define what sort of adversary you're even thinking about. And so we're going to consider a worst case adversary who can perturb a data point up to some specified threshold epsilon, which we call the adversarial budget. And so we can represent the adversarial training problem as an optimization problem in the following way. We're still trying to minimize over subsets of RD, but now our misclassification score is J epsilon, where J epsilon is going to be the expected value of relating to the distribution of the training pairs. And then instead of comparing the label assigned at X with its associated label Y, we're instead able to, or the adversary chooses a neighboring point X tilde that maximizes the difference between the label at X tilde and the label associated with X. So instead of comparing the labels at X with the label assigned to X with its true label, you compare the label of a neighbor of X with the true label of x, y. And so minimizers of this problem, these are called adversarially robust classifiers. And so if we compare with the Bayes classification problem from before, we can see that truly the only difference is this supremum and the fact that we are evaluating this characteristic function at x tilde instead of at x. And so in this kind of expectation version right here, it's kind of hard to see that there is some really nice underlying geometric interpretation of this problem. And so my advisor and some collaborators were able to show that you can also write this formula J epsilon as the expectation of 1ax minus y. So this is exactly that kind of Bayes classification risk, plus a regularizing term that we call the epsilon perimeter, where the epsilon perimeter penalizes all points within distance 2 epsilon of the decision boundary, either according to that row 0 or according to row 1. So the idea of what's going on here is that there's some kind of inherent misclassification that you will have based on your choice of classifier. So that's going to be this first term. This is just how bad you are based off of what you label 1 and what you label 0. But then the second regularizing epsilon perimeter term, this really encapsulates the impact of the adversary. And so because we have defined our adversary to only be able to affect points that are within distance epsilon of each other, well, then it's going to be localized to the decision boundary where we change from class 1 to class 0. And so this is an optimization problem. And one of the kind of first questions you want to ask about optimization problems is about the existence and uniqueness of minimizers. And so my advisor and some collaborators were able to prove that there is, in general, a solution to the adversarial training problem. We call it A epsilon star for a specified adversarial budget epsilon. However, we cannot necessarily expect these minimizers to be unique. And so here's an example of why we would not expect these to be unique. So if we imagine that our entire space of data points is just 4 different data points, where these two up here, based on their row 0 and row 1 densities, these want to have the label 1. So these are more likely to belong to class 1. Whereas the 2 down here, these are more likely to have the label 0. Well, all that matters is that we have kind of the region of radius epsilon around each data point labeled correctly. So one option would be to take just the 2 balls of radius epsilon around the 2 points that we want to label 1 and have that be our classifier A, and then set everything else as belonging to class 0. And on the other hand, we could say, well, we could do the same thing for the 2 points that want to have label 0, where we say a complement is everything in the 2 epsilon ball around these 2 data points. And then everything else is going to assign the label 1. And so, of course, kind of anything also in between these 2 sets in terms of inclusion would also be a minimizer of the adversarial training problem. So especially when there is not density everywhere, there's a lot of freedom about what these sets can look like, and the problem can become degenerate. So now I want to talk a bit about my convergence result. So for convergence, I'm really thinking about taking that parameter epsilon to 0, so that's that adversarial strength, and comparing it with the Bayes classifier, which in some sense you can think of as epsilon being 0. And so kind of the prior state-of-the-art result before what we did, there was a gamma convergence result done by Bungert and Stinson. And so they said in a set omega of RD, then with some mild assumptions on the row I, specifically that they are bounded and of bounded variation, and that at least one of them is non-zero everywhere, then the energy J epsilon converges in the sense of gamma to J0 as epsilon goes to 0. And then because of that, any sequence of solutions to the adversarial training problem possesses a subsequence that will converge to a Bayes classifier minimizer. And this is all done in the L1 topology. And so gamma convergence, if you're not super familiar with it, that is just kind of the minimum requirements for the minimizers of these two functionals to converge to each other, given that the functionals themselves converge to each other. The other comment I want to make here is that about the L1 topology. And so this is really the natural topology for perimeter type problems. And so in kind of that regularized form, we have this epsilon perimeter term. And that's called a perimeter term for a reason. Although it's not quite perimeter, it's a flattened perimeter, it does share a lot of the same properties. And so it is relatively expected that you can get convergence in the L1 topology. The convergence result we were able to get is that under the assumption that the rho I are continuous and bounded with still that kind of non-degenerate rho 1 plus rho 0 should be greater than 0, then our adversarial minimizers will converge uniformly to our Bayes classifiers locally as epsilon goes to 0. And so the uniformly here, this is really in the sense of like the maximum distance between the sets. So we're able to constrain the distance away, or the distance between A0 star and A epsilon star. And notice that our assumptions are really similar to the previous one, with the main difference being their densities had bounded variation, whereas ours have to be continuous. And so the strategy here is that we can essentially corral the adversarially robust classifiers to be within a specified distance, eta, of the Bayes classifier, such that when we take epsilon to 0, then the distance eta will also shrink to 0, meaning that the adversarially robust classifier, A epsilon star, will converge to the Bayes classifier. And so pictorially, you don't need to understand everything that's going on here, but what I'm trying to show is that you can imagine these blue regions as being the regions where we know that our adversarially robust classifier cannot be. So the boundary has to be between these light blue sets, and that's represented here by the green boundary. And then the boundary of our Bayes classifier, that is going to be that black boundary here. And so the result that we were able to show is that using the corralling argument and under those mild assumptions, then the Hausdorff distance between A epsilon star and A0 star will decrease to 0 as epsilon goes to 0. And we're able to show that that convergence rate is at most big O of epsilon to the 1 over d plus 2. I do want to note this is not expected to be the optimal rate of convergence. We would expect it to look more like big O epsilon. And that's something that we're definitely thinking about showing in future work. I want to finish my talk by giving a little bit of an intro about the regularity to this problem and how we think about it. So first of all, kind of the result that stands right now is that under some mild assumptions, there exists a C1/1/3 minimizer of the adversarial training problem, where the way we think about regularity here is we think about the functions that can represent the boundary of our classifiers. And so as an example, we can look at the difference between this boundary of the set A1. This is a circle, and everywhere the boundary can be locally represented by something that we can take derivatives of. However, if we think about the set A2, which is now two balls that have a tangency right here, near this point of tangency and at this point of tangency, you cannot locally represent this boundary by a differentiable function because there's a cusp. And so this is kind of some of the behavior that we are trying to rule out when we're hoping to improve this kind of C1/1/3 result to look something more like C2, meaning that we can take two derivatives and they're continuous. And so in addition to thinking about the boundary of our adversarial classifier directly, it's also helpful to think about the boundary of our sets R0 and R1. So these are sets that are just kind of a specified distance away from our boundary of the classifier. We can kind of like push forward results that we get about R0 and R1 to A, and R0 and R1 have some nicer properties to make them better to study. And as kind of back to the motivating example, if we consider this rho 1 minus rho 0 is equal to the product of x1 times x2, if we think about what the adversarially robust classifier would be for an epsilon greater than 0, well, if we just consider that Bayes classifier is the candidate, which is this light blue set beneath everything, including this dark blue set as well, then notice that there is a corner here at 0, 0. So there's already a point where we would not expect it to be differentiable. So hopefully, if these minimizers can be C2 in general, this is not going to be a minimal energy classifier, and there is something better. And so some of the questions that we ask here is, so again, not just what is the regularity for A, this light blue set, but what regularity can we expect for R0 and R1? Because notice R0 and R1, they also have corners. We can also notice that there is some amount of, we call it a matching between the boundary of R0 and R1, where there are points distance epsilon away, if you look at the boundary of A, in the boundary of R0 and R1, except again, kind of for those points right here that are near the singularity. That's kind of where we're missing that. They're exactly points distance epsilon away. And so this matching between R0, R1, and A, is that matching always going to be unique? Notice that the points where this uniqueness breaks down is exactly going to be your corners of R0 and R1, where this corner here matches to two different points. And so some tools to think about this, we've really been thinking about representing kind of these boundaries as differentiable functions, where we represent one boundary as one differentiable function, this other boundary is another one. So that way we can take derivatives here and then hopefully learn something about what's going on at the corners there. So that's all I wanted to talk about today. Here are some references. Thank you so much for your attention.